Okay, good evening everybody. Thanks for coming to listen to this consensus in blockchain presentation of mine. Today, the goal of this presentation first is to kind of describe what consensus is. First we will go with the problems it comes with, what blockchain resolves with this consensus, and why we should appreciate it. I would like to say that the concept of this presentation was made so that everybody can understand. So I will not go very deeply into how the tech works. I will just on a high level explain it. And later on, if you guys are not kind of want to go deeper into it, you can just stop me and ask me questions. So you can really, during the presentation, stop me. All right, so this is the agenda that we have today. So first topic will be attacks in blockchain. So we all understand that blockchain kind of resolves this centralization problem that we have, but we kind of don't know all the problems that it resolves. And I think that we first need to understand what the problem is in order to appreciate the solution. Second topic will be breaking down into a blockchain consensus. So in this part, I will just explain what the consensus is, and in blockchain, what 3 questions we should ask ourselves in regarding when we are kind of designing a consensus algorithm in blockchain. You know, there's 3 distinct things that we need to care about. Then, of course, I will talk about proof of work and proof of stake. We all know that proof of work, you work on something, but we don't know actually, rarely anybody knows how it actually works. And I believe this is very important, especially for us who are working in this branch, to understand actually how it works and the game theory behind it. And in the end, we will have honorable mentions. And here I just placed a proof of authority consensus algorithm, and I will explain you how it actually functions and where it can be implemented, and why it's actually okay to have a proof of authority blockchain. And in the end, we will finish with a Q&A session. All right, so what attacks can happen in blockchain? There are several types of attacks in blockchain, and one of the major ones is Byzantine generals problem. I will explain later on what this is. The second and most common one is DDoS attack, you know, the distributed denial of service. It exists even in the centralized servers, like it can just bring the whole system down. We will talk about the civil attacks, where in the peer-to-peer network somebody pretends that are many, like they're impersonating many profiles, and all those profiles are kind of tied to one centralized personality or authority. And this one is proof of work specific, which is kind of a 51% attack. And everybody knows about that, but we will go deeper into it later on. So, Byzantine generals attack. Okay, this is a problem that was first kind of stated back in 1982. It kind of is a game theory problem that explains like what the centralized distributed and decentralized system needs to solve first before they can kind of what problem they have actually. And at that time, this problem was unsolvable because they didn't have protocols in order to that would kind of speak to each other. Like, and second thing, this was like the first, I guess. It started back in 1950s, but first time this game theory was introduced in 1982. So let's go like this. Imagine that you have a castle, and that castle is a villain, all right? Now you have generals around that castle that are gonna attack that castle, all right? Now, in order for us to kind of win in this and penetrate the castle, we all need to be synchronized and coordinated. What that means is that everybody needs to know what is the strategic plan. Let's assume that these generals and their army was kind of fairly far apart distributed, and in order for us to know what is the plan, we need to kind of send the messages, all right? So we send a message from one general to another, and then so on and so forth. Now, there is a problem here. The problem is that we don't know since the generals and their army is sufficiently far away, we don't know if our message is going to be intercepted or not. Like we can send it on a horse or whatever. We don't know if it's going to intercept it, and how are we going to know that our message is received? So that general who received the message also needs to kind of send the message back that, hey, we received your message and we agree with your plan when to attack, what, and how to attack. Second thing is, we have traitors. We don't know who those traitors are. And remember, we can only penetrate the castle if we all cooperate together. Now, the solution to this problem is, I would say, quite simple. But I would say it wouldn't help like the Byzantine army, but it would help in the IT. So how we solve this problem? Well, each general has a ledger of events that is synchronized with the whole set of generals. And they all send messages between themselves, like so on and so forth, all right? If I send a message to somebody, that message is also relayed to all the peers, all right? To all the generals, let's say. Second thing is, there is no commander of the whole army. There is no central party. So everybody needs to make a consensus when they receive a message, what they agree and what they are not agreeing on. In terms of blockchain, so every time a block is, for example, mined or validated, all the participants should agree on what happened and in that block and execute the kind of order of events for the last block, which is a couple of minutes or seconds. All right? So it looks like this. How is it resolved? We all talk about the distribution of a blockchain. So this means that every node has its own ledger. This is how it started. This is the solution to this problem. Everybody has all the messages sent, and they are written in this ledger. Sent and received, of course. Now, for the second problem, we have the distributed denial of service attack, which is kind of a very common attack happening in the IT, where one party, let's start with just denial of service. Let's just say one party sends a lot of requests and the server breaks down. Let's translate it to some kind of, let's say, for example, I can memorize 10 items or things in 10 seconds, all right? Imagine now that somebody tries and give me to memorize 20 or 30 items in 10 seconds. I would just shut down, am I right? I can make it. That happens to servers with this attack. Now, that is denial of service. You can fight that by just, for example, you realize which IP address kind of sends a lot of requests, try to spam your server, and you just block it. But there is a second thing, which is distributed denial of service. And it looks like this. So you have one authority, one party that kind of distributes, let's say he deploys on several servers this kind of a spamming bot, all right? And now you have who knows how many clients kind of trying to send a message to your server and kind of request some service and stuff, and again the outcome is the same. Now, how do we fight this in blockchain? So you remember, like, what are the main kind of components of blockchain when you want to do transaction? First, we know that it's a distributed ledger. All peers inside of this system have the copy of the ledger. Second thing, we know that we have fees. So now, when we introduce fees into the system, we can kind of, the attacker can allow himself to spend a lot of money in order to attack our system. And it might even not be feasible at some point. So the fees kind of is the main defense against the denial of service attack. Now we come to the interesting one, which is kind of a Sybil attack. So a Sybil attack is an attempt to manipulate peer-to-peer networks by creating multiple fake entities, all right? And how does that hurt a network when this thing happens? When it can influence the outcome. For example, it can influence, like, imagine a Twitter account, and let's just say Twitter targets you and spam you with a false information. It can influence your judgment, you can kind of get a false information of the event or stuff like that. It happens in the real world and it can cause a lot of problems. Now, in a peer-to-peer network such as a blockchain, the problem here is that I cannot send messages to honest parties. I'm surrounded with dishonest parties, and it can influence. So it can influence what I'm gonna like my perception of the whole blockchain. And then they allow me to send a message to honest parties, and that message will be biased. All right, and of course not true. So it looks like this. So you have entities in the form of clients or nodes, whatever. Let's say this is our nodes and this is a honest node. So let's imagine that we are attacked by a Sybil attack and we cannot kind of we cannot exchange messages with the honest nodes, all right? Now, so they will kind of relay to us a messages that is highly biased. We kind of get like say, all right, this is the truth, and then we relay that message to the honest parties, which is not in line with what is actually happening, all right? And how we manage this? Well, we kind of, in a proof of work system, there is no kind of solution for that, because you can have a miner, you can have a miner, and on that miner you have a node, and you can try to do that, and network realizes that you did that, and they kind of fork you from the network, but then you can just reset your miner and try again. But in the how we fight this in the proof of stake system is that we locked, in order to get identity here, you need to lock some funds. And now, if you kind of try to do some fishy thing, you get slashed, all right? And this is how we fight. This is how we fight this Sybil attack in the blockchain space. All right. And now, of course, we have a 51% attack, which is self-explanatory. It has to do with our longest chain rule, but I will talk about that later on. The only thing for now you need to know is that if you possess 51% of the network's hash in a proof of work, you can kind of reorganize the chain and you can double spend, all right? All right, so breaking down blockchain consensus. In simpler terms, consensus is just a dynamic way of agreeing between parties, all right? We all experience that in a very primitive way, where we, for example, we go on meetings and we talk to each other and we come to a consensus, we do some kind of workshop and stuff like that. Let me go a little bit down and explain this. Imagine like that we are 10 of us around the table, all right? And when we want to decide on something, for example, we want everybody to agree on a certain set of rules that we set before even we join this kind of system, all right? So the three questions that we need to ask ourselves is, in regards to blockchain. In the distributed system like blockchain, you need to answer three questions, and those are, who can propose the next change to the state of a blockchain? And I first want to explain what the state of a blockchain is. And it's pretty simple, and I believe everybody knows what state is, but for the non-technical people, let's say like this. You have, for example, a balance. Let's just say account, sorry, can you see? Okay, account number 1 and account number 2. All right, that account has 7 Ethereums. Sorry, I'm lefty, but I hope you see everything. And let's say account and account 2 has 5 Ethereums. And let's call this state state A. All right, this is state A. Now the transaction comes. All right, or set of transactions that says, for example, send from account 1 3 Ethereums to account B. And now you have a state transition that transits from state A to state B, where you have account 1 has now 4 Ethereums, and account account 2 has now, what did they say? It has 8 Ethereums. Okay, what you need to remember here, it's pretty simple. So you have the state that is kind of currently static. You input some things that happened, for example, and then you have the next state, which is state B, all right? In the blockchain terms, it's like you have a transaction, it happens something to a state, and it transits to a state B. Now, who can do that? Who can kind of propose for this to change? We will talk in this section. In the next section, sorry. Which set of changes is final? Now, you maybe never heard about the finality in blockchain, but I will tell you that in some cases, you have several proposed blocks at the same time. Which one are we going to kind of add to a blockchain in a canonical order? This is what we next need to kind of ask ourselves, and I will explain that later on for the proof of work and proof of stake blockchains. And then what happens if someone breaks the rules, all right? This is the most important stuff. We need to have some safety catch if somebody tries to kind of, I don't know, double spend or trying to mine an invalid block or validate an invalid transaction, whatever. Now, in Polkadot world, and not only Polkadot world, in blockchains that are not monolithic, all right? You can separate these three things, but for example, in blockchain, all these things are smudged together, and I'll explain how. All right, now we go to a proof of work. Now, the first question was, who can propose the next change? I say a miner. Now, you should ask me, of course, what the hell miner does and how does he get the privilege to do that? Well, I'm glad you asked. I hope that is your question. All right, so now I will go deeper into how this is actually done, because we all know miner does something, but ask yourselves, do you really know what is being done below the hood? All right, so now we have how the proof of work and what miner does is he does this. You have a block, he prepares a block, all right? How he does that? For example, let's say we have 3 nodes, all right? Node A, node B, node C. Let's say one transaction comes through this node and it has to be propagated between this one and this one. The second and third transaction comes through this node, same thing happens, all right? And let's say the fourth transaction comes here, and it again gets propagated to the node A and B. Now, what miner does is, now they all have the same, it's called a memory pool. You keep transaction in the memory pool until you validate them and add them to a blockchain, all right? When you add them to a blockchain, then you delete it from there. What miner does? He takes, for example, cherry picks, let's say transaction 1 and transaction 2 and transaction 3. Let's say he leaves it out, all right? Transaction 4 he cannot put in the block. Now, first thing I need to explain, you have a header of a block and you have a transaction or a footer of a block. In a footer of a block, you have all the transaction packaged, all right, that are being included into this block. That when you mine it and when somebody else validates it, he just goes through this and updates the state that I just explained what it does. So something happened, I need to update the state, blah, 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 all right? And for example, let's say the miner C put in a block transaction 1, 2, and 4, while the miner B puts transaction 2, 3, and 4. Just so you know that miners can cherry pick the transaction they want to put in a block. They don't need to be synchronized in that way, all right? So, what the miner does, as we say, he puts the transaction in a block footer, then he do some kind of computation which is called a hash, and he gets this Merkle root hash, all right? You don't need to, just remember that he takes all the transactions in the block, put it through some function, and he gets this Merkle root hash. Then you have 5, actually, I would say static, but static values here, and the only one that is variable is this called nonce or number used once. So now, what the miner does, he tries to take the whole header of this block and randomly chooses the nonce, go through this hashing function, and then computes the hash. Now, when he computes the hash, he should compare it to the max target or the difficulty, all right? So what is the difficulty? For example, if you have a hash that is, let's just say, the difficulty goes from 0 to 10 on 77, so like it's a huge amount of numbers, all right? So what we are trying to achieve, we are trying to find a nonce that when we hash the header of the transaction block, of the block, it's below the max target, all right? If it is below the max target, you can send to other miners to validate this, and then they go through the execution of all these transactions, check the header, check if the nonce is correct. If it is, then you write it to the block, all right? So this is how you kind of get, this is how you get a, how should I say? How you get a turn to propose the next change, all right? You play a game, you win a game, and then you can propose the next change to the state. Now, which set of changes is finals, all right? Now, imagine the scenario where we have two miners kind of mining the block. So two miners that the maximum difficulty falls below the one that we kind of determine as a network. In this case, all nodes write both networks, but they are not finalized, all right? You can only have one block that connects to the whole canonical order, all right? So what we do, this situation is called a tie. So what we do is the miners will start building on the blocks, all right? On the first block they received, all right? The tie is broken when the next block is kind of mined. At that point, the other block is disregarded, and it's called the orphan block, all right? The miner that mined it doesn't get reward. That's the point. It looks like this. So imagine you have blockchain, and then at one block you have two miners mining the correct block, and then we extend that block by, for example, mining on the continuing to mine and create the block on the first one we received, and then we check if 51% of the miners mine the block on this one, then we disregard and we call it the orphan block. All right. Okay, what happens if someone breaks the rule in proof of work chains protocols? Well, nothing. You can just, as I said, you can just reset your machine and try again. All right. So this is kind of the thing with the proof of work that doesn't work very well. You know, I saw many. For example, in Ethereum Classic, there was 2 or 3 days of constant attack. You know, in proof of stake, that cannot happen, because if you attack the network, you get slashed, and that is the main difference here. Okay, now we go to the proof of stake consensus mechanism, and I will focus on only two. There are several kind of mechanisms available or being developed. One of them was made by Tendermint or Cosmos, you know, but this presentation will go so long that I don't know when I would finish it, all right? So the first one is called Babe, and it's kind of Ouroboros-Prowse variation. So Ouroboros-Prowse was developed by a company called IOHK, and they also developed Cardano blockchain. They were the first ones who had a really, really good implementation of proof of stake system. And first implementation is Ouroboros-Prowse, and the next iteration that they're currently running on, it's called Ouroboros BFT, or Byzantine fault tolerant. The second one, we will look at the Ethereum's proof of stake consensus algorithm that's called Gasper, all right? Now, these two distinct proof of stake algorithms are really, they have a lot of similarities, all right? But I must say that the Gasper is very, very complex, and I won't go deep into it because it's very complex. Okay, Babe. This is a block production engine, And it's inspired, as I said, by Ouroboros Praos and used by Polkadot/Kusama and all kind of ecosystem users that are building on Substrate, I suppose, if they didn't implement their own proof-of-stake algorithm. So it can be used on its own, or it can be coupled with, it's called a finality gadget called Grandpa. And I'll explain how Grandpa works. It's currently amazing. The thing here is, because this is not a monolithic chain, this is a modular blockchain, we can do that. We can separate the finality from the block production. And by doing that, we kind of increase the efficiency, because we don't need to send, we create block, but then we send to every node, and that every node needs to send to everybody. No. Like when you create a block here, you just send it, and the nodes that receive it doesn't need to send it to everybody, all right? Okay, Babe is a slot-based consensus algorithm. It breaks down into epochs and slots, all right? What that means is, like, you have an epoch that is, epoch, that is, let's say, in Polkadot term, it's 24 hours long, all right? And in those 24 hours long, you have slots. So slot goes every 6 seconds, and in every 6 seconds, you create a block, all right? So in each block is validated by a different validator, all right? And how do we go to, again, the first question we have, who can propose the next change to the state of the blockchain? So each slot, so remember, we have slots, and then we have epochs, all right? Why we have epochs? Because in Polkadot, for example, you have 500 validators, but only 300 can validate during the epoch. So each epoch, we switch the validators, all right? We change the set of validators. So each slot have a primary and secondary validator. Why do we have this? Because we again determine who's gonna create blocks on a function, and that function can kind of give you a number that, can give you some number that no validator can have, you know. And this can make a problem. And if you don't have a validator who's going to validate a certain block, then you need to have a backup, and that backup is called a secondary validator. All right. So first, what is a primary slot validator or a leader? So primary leader is kind of decided by using the verifiable random function, all right? So you need to know about this verifiable random function. Nothing is kind of random in the blockchain space, because if it's truly random, how can you prove it that it's random, all right? But it's kind of somewhat random. So how it works is you have some parameter, same as hash. You take, let's just say, your private key, your block number, and let's just say timestamp, I don't know. There's many things, all right? And then you output some number, all right? And for example, we have a threshold, same as difficulty in the proof of work. So if the number that you got from the VRF is below some threshold, let's say 20, then you can validate that block, all right? So this is just the kind of, you have a verifiable random function, you put some input, if that input is lower than the threshold that everybody agreed upon, okay, I can validate block. Now, what happens if 2 or 3 maybe validators get the number that is lower than 20? Then all of them can make a block. And then we have kind of in proof of stake, you have several potential blockchains, and I will explain how it looks. All right. Now, the secondary slot leaders are there in case nobody is there to validate the blocks. For example, if nobody got the random number that is lower than a threshold, all right? Then it's a kind of, it goes with a round robin, like you get, for example, you're a secondary option, you get like you're a secondary option at that block, or et cetera, all right? And it's already known during the whole epoch, you're known which block are you gonna be secondary option for, not like this. So, yeah, first I want to say one thing. Now, as I said, there are several, like, this PRF like there are several validators who can get the number that is below the threshold, all right? If that happens, like every validator's block is valid, but we are watching for this. So these are potential kind of blockchains. Imagine it as a potential blockchains. We have finalized blocks, and they are just linear, all right? The part when it's not finalized, all right, what validator do, they get the messages from, let's just say, several validators who can validate this block, and they put them like in order, like this. Like, for example, after this finalized block, I got 3 validators that produce block, and they put them here, all right? And then so on and so forth. Now, in Babe, there is also a probabilistic finality, or Ouroboros Praos. There is a probabilistic finality that says we can potentially finalize block that has the most primaries, all right? So if you look here, if this block is finalized, all right, then we disregard this whole potential blockchain that could have happened, all right? Because it doesn't build, this blockchain doesn't build on the finalized block, but it builds in the lower one, all right? Now we look at this one. Okay, on the finalized block, we built 5 blocks, but 4 of them have the secondary validator who produced the block, all right? On this one, we have 2 secondary and 1 primary. And on this one, we have all primaries that produce the block. In this case, we add this potential blockchain to the canonical order, and then all these 3 blocks are finalized, and we start building from this block here. So we can start again, all right? If you have questions, please, this is kind of a little bit maybe advanced. Please stop me and ask me questions. All right, so which set of changes is final? Well, in Babe, we have it's called the Grandpa's Polkadot Finality Gadget. And it is a deterministic way of how to finalize block, all right? We just presented probabilistic way. We expect at some point that all these blocks will finalize, depending on the rule that I said, all right? But with Grandpa, it's deterministic, and I'll explain how it functions. All right. Okay. How does it work? So you have, as I said, you have a block production disconnected from finality of the blocks. How does it work? Well, first, a node that is designed as primary proposes the highest block that he thinks it's finalized. And I will kind of draw this so that you can visualize, all right? Because this is a little bit advanced. Okay, let's imagine this is blockchain. These are all finalized blocks up until here, all right? Up until here, and then we have potential, wait, let me just, sorry. So we have we finalize all the blocks until here, and then we have potential forks. Let's say like this. And let's imagine that in this blockchain, we have 3 validators, all right? Validator 1, validator 2, and validator 3. And now we will go through this. A node that is designated as a primary broadcasts the highest block that it thinks could be the final from the previous round. So let's just say I'm the primary, and that's node number 1. And I say, I think, and I propose, I vote on these blocks. I vote on these blocks, all right? I vote on these ones to be finalized, all right? Now that decision is being broadcasted through the network. And after waiting for a delay, all right, each of these validators, in our case, we have 2 validators, vote on which block they think that should be finalized. For example, let's say validator number 2 votes for, so this is vote of the validator number 1. He votes for all 3 of the blocks here. But validator number 3 believes that only this block should be finalized, all right? Now, in order for a block to be finalized, all right, and written in the blockchain in a canonical order, you need to have 67% of the stake amount of tokens being voted on the block, all right? Let's imagine, for the simplicity's sake, that all three validators has the same amount of stake, all right? In this case, let's say they have, each of them, they have 10 of the tokens staked, all right? In this case, this block was voted on twice, and it's 20 out of 30, which is 67%. This block also was voted 20. This block is voted 10, and this block is voted 10. In this case, what Grandpa does, he says, okay, 67% of the validator stake voted on this block, which means that these blocks are finalized, and the other ones you can disregard, all right? These two blocks are finalized, and you can build from this block. So this one can kind of have now, I don't know, 3 more blocks built upon. And the process continues, all right? So in this case, you disconnect the block production from the finality. If you want me to repeat, please ask me, all right? Did you understand anything? Okay, all right. By the way, there is a process here. So each validator votes, and then there is it's called a pre-commit. For example, when every validator receives the vote of other validators, they say, okay, 67% of validators vote on this finalized block, and I will commit to it, and then I send pre-commit to everybody, and then I finalize the block when I see that everybody, at least 67% of validators will kind of vote and accept these blocks.
Maybe in this situation we can talk about like gossip protocols, for example, in order for the validators, how they decide, how they gossip between each other, which is the finalized last chain, for example.
Yeah. Okay, I mean, I believe that this is a kind of a topic for the next iteration, and it's very complex, but you have a you have libp2 library, P2P library that is handling that, but kind of validators, they all need to exchange information. If you remember from beginning of my presentation, in the Byzantine fault-tolerant system has to kind of send messages to everybody, all right? In this case, in order to block to be finalized and also to produce blocks, especially block to be finalized, you need to kind of talk to everybody, all right, in the system, all right? See, okay, what is this node voting on? What is this one? What I am voting on? And then you get the unbiased opinion what is happening on the blockchain. It looks like this. So we have, this is what I actually draw, sorry. So you have, these are finalized blocks, and then on block C, you have the block that is created, like 2 blocks that were created, you know, like there were 2 validators that created block at the same time, and it goes like this, and this just explains the thing that I just drew, more or less. Okay, what happens if somebody breaks the rule in proof-of-stake systems such as BAPE? Well, they get slashed some portion of their tokens, all right? Of course, that makes sense, am I right? And this is kind of very good solution to the Sybil attack problem that we were talking to, because now what makes validator, first of all, what makes validator get slashed? First, producing blocks that are invalid. Second thing, going offline, not showing up when the turn is to validate blocks or do some other stuff. Voting on several blocks at the same time. So during of the same height, sorry, that wants to be finalized. For example, I cannot, in this case, vote on both of these. Let's say I'm validator 1. If I vote on this block and this block, these are of the same height, I will get slashed. It is not allowed, all right? I cannot bet on two blocks. I can only bet on one. And there are several reasons for that, but I'm not going to go deeper into it right now. All right, and lastly, all right, there is a Gasper protocol, and it consists of two components. First is Casper, the friendly finality gadget, and the second one is ghost fork choice algorithm. So together these components kind of are making the whole consensus system of Ethereum network. And they're handling fork choices, finalization, stake, slashing, everything, all right? Okay, who can propose the next change? Again, the same question. Who can propose the next change? Where? It's kind of similar as in Babe, in a way that like you have, again, a random number algorithm. In this case, it's called RANDAO. And it mixes, again, some inputs. And those inputs are kind of a little bit different. But the same outcome is, there is the same outcome. So the thing here is that only one validator can validate the block in the Casper, all right? In the Gasper. So in this one we computed a random number, and then we compare it if it's below the threshold, if it is, and then you can validate. Several people can get a random number that is below the threshold. In this case, no. You get a random number, and kind of the whole network decides who's going to be a validator there. And by the way, the Gasper, it's kind of still incomplete proof of stake algorithm. It's so complex, guys. I cannot like even comprehend like how they are handling some kind of data availability stuff, some kind of attacks that I just want to kind of leave it out of this topic because I wanted to make a more or less high level presentation that is kind of not very high level as I expected to be. But what to do? Okay, which set of changes is final? So in Polkadot and, Substrate world, we have this grandpa. We know how it finalizes the thing, but in Ethereum, it works a little bit different. Same, but different. So you have, let's just say you have, again, let's say, again, until here it's finalized. From here you have some kind of forks. All right? And now, like what validators do is they, again, vote on the block that they think should be finalized. And again, 2/3 of the system needs to agree. And let's just say, for the sake of it, that this is the block that is being voted on. In this case, that block is now justified. It's not finalized yet. When is it finalized? When somebody builds a block on it that is justified, if you know what I mean. So it's justified until another block built on top of it is justified. In case this block is justified, built on top of it, then this block is kind of finalized, and it can be written in the blockchain. All right. It's again there are some kind of stipulations. Of course, again here you get slashed for double voting on several blocks of the same height and stuff like that. And it's really not economical to try and do this stuff. All right. Okay, we said again, how can you manipulate this? First of all, of course, we said 67% of nodes need 67% of staked Ethereum needs to vote on that block that should be finalized. You can achieve that if you have 2/3 of the staked Ether, which is impossible. I guess not even states can buy that much Ethereum unless they crash it, maybe. And second thing is that destroying at least 1/3 of the total stake amount, which can happen if, again, you are voting on 2 blocks, for example, you are inactive and stuff like that. All right. Okay, what happens if somebody breaks the rules? Again, same. So you get slashed. And what makes validator get slashed? You propose the wrong blocks, you are inactive, voting on several blocks of the same height that is not allowed and stuff like that. And now, for the honorable mentions, we have a proof of authority consensus algorithm. And this is kind of a different concept, all right? In this consensus system, or blockchains that are using this proof of authority system, you are not staking tokens, all right? You're staking your brand or whatever. Like, this is good, for example, banks. Let's just say banks want to collaborate between themselves, but they don't want to go and transact on a public blockchain. They just want to make their consortia, all right? Consortia of validators. So what they do is they create a blockchain, they use this consensus algorithm, and for example, in this algorithm, each block is already decided who's going to validate. It's a round robin, all right? What is at stake here, for example, what prevents, in this case, validators to kind of do something bad is their reputation, all right? They stake their reputation. So for example, imagine there is an energy web chain, all right? And in energy web, that is a proof of authority, in my opinion, most famous proof of authority blockchain. And there are validators such as Shell, Tesco, Tanaka, Engie. Those are very, very famous multi-billion-dollar companies. Imagine they want to try to do something. They would lose billions overnight, all right? So this only works for those kind of cases. And we don't need to ask those three questions now, like they're literally answered. Who can be a proposer of a block? Well, that is decided in a round-robin fashion. Finality is automatically considered, all right? The other validators just need to check if the block is correct, all right, everything is correct inside, and just add it. And the third thing, punishment, if somebody breaks, it's kind of in a form of reputation degradation, all right? And that's that. All right, so thank you for listening. If you have any questions, now is a Q&A session. If you have any questions, please do ask. I really hope that this is a high level, but at some point it wasn't. But what to do? Thanks. Okay, and any questions? Great. Okay.
Okay, given the fact that you know both Ethereum and Polkadot, and how the finality, production of the blocks and the finality is achieved in both consensus mechanisms, and knowing that in Ethereum you have the execution layer and the consensus layer, which one do you think is more accurate on the finality of the blocks? So Ethereum or Polkadot, in your opinion?
Finality on the blocks, well, I don't, I believe that Polkadot is faster, but I believe that Ethereum might be safer, all right? Because they go through a lot of checks before you finalize some blocks, all right? In Polkadot, you can finalize several blocks in one round. In Ethereum, you cannot, it just goes, like I first finalize this, then this one, and stuff like that, all right? I mean, Ethereum and Polkadot are extremely well thought of, Babe and Gasper are extremely well thought of protocols. However, considering the complexity when you get out from the consensus part and you get through sharding, all right, I believe that this complexity, I would give advantage to Polkadot, because in Ethereum, all shards have the same kind of execution layer and are validating more or less same type of transactions. In Polkadot, every parachain or shard has a different type of, different type of transactions, different type of block production, block production that you need to validate and stuff like that, all right? So that's what I think. Okay, thank you very much.